Take a moment before we begin and let the day finish. Whatever it brought, it's behind you now, and the only thing on the schedule for the next few hours is rest. Let the weight of your body settle into wherever it has settled. Let your hands rest open if they want to. Let the back of your head sink a little further into the pillow. Let the small alertnesses of the day fall away, one by one, the way they fall away every night around this time. You won't need to remember any of what follows. That's the arrangement of these recordings. If you fall asleep 2 minutes in, the story keeps telling itself, and it'll be here when you come back. If you wake up later and have lost the thread, that's also fine. Nothing on the other side of these hours depends on you holding on to anything. The story tonight is about programming. Most people, at some point in their lives, have had a friend, or a relative, or a coworker who they knew was a programmer, and have nevertheless had no idea what that person actually did all day. Programming, as a profession, is one of the more invisible major activities of our era. The programmers go into a room. They sit in front of a screen. They type. Hours later, they come out. Something the rest of the world uses now exists or works better than it did before, but the actual content of what they did remains, for almost everyone outside the profession, a kind of polite mystery. That's what tonight is for. Not to teach you to program, or to fill your head with technical terms, or to give you a quiz at the end. Just to walk you, slowly and gently, through what the activity actually is. By the end of the story, you will know, in some real sense, what programmers actually do. Not in the sense of being able to do it yourself, in the sense of finally understanding what the thing is, what the activity consists of, what it feels like, why it exists, why anyone would choose it as a way to spend a life. That's the promise of the title. We're going to actually do this thing. Just one small thing before we start, and then I'll stop asking anything of you. If a voice like this in the dark is the kind of thing you'd like to have around when sleep is slow to come, you can subscribe before we get into the story, and the next time you can't quite settle, the next of these will be waiting for you. And if you have a moment, leave a note in the comments about where you happen to be tonight. It turns out to be a quietly nice thing. Scrolling through later and seeing notes from people in dozens of cities, in their own rooms, in their own long nights, listening to the same slow voice. No obligation, just if you want to. That's it. That's the whole ask. The story we're going to tell begins more or less in the 1840s, in London, with a young woman named Ada, who was the only legitimate child of the most famous poet in England, and who had decided, against everyone's expectations, that what interested her in the world was mathematics. Chapter 1. The first program ever written. Ada was born in December of 1815. Her father was George Gordon, Lord Byron, who was at that point the most celebrated poet in Britain and also one of the more scandalous public figures of his generation. Her mother was Annabella Milbanke, a serious-minded woman from a respectable family who had married Byron a year earlier in what nearly everyone around them had warned was a mistake. The mistake was confirmed quickly. Byron, whose temperament was not suited to marriage, left England a month after his daughter's birth. Ada never met him. He died in Greece of a fever when she was 8. Ada's mother, Lady Byron, was determined that her daughter would not turn out like her father. She had concluded, with some help from popular Victorian theories of the time, that the wild emotional excesses of poets like Byron were caused by a lack of mathematical discipline in their upbringings. Mathematics, in this view, would calm the nerves and order the mind. So Ada, from the age of 4, was given a relentless mathematical education by a series of tutors. She studied arithmetic. She studied geometry. She studied algebra. She studied the celestial mechanics of the moon and the planets. She was, by every available account, very good at it. In June of 1833, at the age of 17, Ada attended a party in London, where she was introduced to a man named Charles Babbage. Babbage was a fellow at Cambridge and one of the most eccentric scientific personalities of his time. He had been working for several years on a project to build a calculating machine. The machine was called the difference engine, and it was an enormous mechanical device, partly built. That was meant to calculate mathematical tables using a system of brass gears and rods, without any human arithmetic involved. Babbage showed Ada a working portion of the difference engine at his home. Ada, by the accounts of the people who were there, was the only person in the room who seemed to understand, on a deep mathematical level, what Babbage had actually built. They became friends. Over the next decade, despite a substantial difference in their ages, they corresponded extensively about mathematics and about the design of Babbage's machines. By the late 1830s, Babbage had moved on from the difference engine, which he had never finished, to a much more ambitious design called the analytical engine. The analytical engine was not just a calculator. It was supposed to be a general-purpose computing machine, capable of performing any sequence of mathematical operations that a person could specify. It would have a memory called the store, where it could hold numbers. It would have a calculating section called the mill, where it could perform operations on those numbers. It would receive its instructions from punched cards, similar to the cards used at the time to control the patterns woven by the Jacquard loom. The machine would, in principle, be able to do anything that could be expressed as a sequence of mathematical steps. In 1842, an Italian military engineer named Luigi Menabrea attended a lecture Babbage gave in Turin about the analytical engine. Menabrea wrote up a description of the machine in French, which was published in a small Swiss journal. The next year, Ada Lovelace, she had married William King, the Earl of Lovelace by this point, and was now Countess of Lovelace, translated Menabrea's paper into English. As she translated, Babbage suggested that she add some of her own notes to the translation, since she understood the machine better than Menabrea did. The notes she added were extensive. The translation of Menabrea's original paper was about 8,000 words. Ada's notes, appended to the end, ran to about 20,000 words. They were, in many ways, the more important part of the document. They explained the analytical engine more clearly than anyone, including Babbage, had explained it before. One of the notes, called Note G, contained something special. It contained, in the form of a detailed table, a step-by-step procedure that the analytical engine could follow to calculate a particular sequence of numbers called the Bernoulli numbers. The procedure was complicated. It required the machine to repeat certain steps in loops. It required the machine to make decisions about what to do next based on the results of previous calculations. The procedure was written down in a precise enough form that, had the analytical engine ever been built, it could have been punched onto cards and fed into the machine, and the machine would have produced the Bernoulli numbers as output. What Ada Lovelace had written in Note G was a program. It was a sequence of instructions in a precise machine-readable form that told a computing machine exactly what to do in order to produce a particular result. It was, by general acknowledgement, the first computer program ever written, even though the computer it was written for did not exist yet, and would not exist for over a century. The deeper insight in Ada's notes, however, was something even more striking. She wrote in Note A about what the analytical engine could in principle do, given that it could perform any sequence of mathematical operations. She speculated that if anything could be represented as numbers, the machine could process it. Music could be represented as numbers, therefore, in theory, the machine could compose music. Images could be represented as numbers. Therefore, in theory, the machine could produce images. Language could perhaps be represented as numbers. Therefore, in theory, the machine could process language. What she had glimpsed in 1843 was that a computer, given enough power, could do almost anything that could be described in a precise enough way. She had glimpsed, in other words, what computers actually became. 150 years later, she was the first person to see it. Ada Lovelace died in 1852 at the age of 36 of uterine cancer. She had had a difficult adult life with persistent illness and gambling debts and a complicated marriage, and her later years had not been happy ones. She had not, in her own lifetime, been recognized for what she had figured out. Her work on the analytical engine had been considered, by the few who read it, an interesting but obscure technical exercise. The analytical engine had not been built. The notes had been forgotten. She was rediscovered, slowly, in the 20th century, as the field of computing came into existence and people started looking for predecessors. By the 1980s, she was widely acknowledged as the first programmer. A programming language developed by the United States Department of Defense in 1980 was named Ada in her honor. Her face has been on stamps. Her notes, including Note G, are available to read online more than 170 years after she wrote them in any web browser. The first algorithm intended for a computer, which is what Note G contains, is still readable today by anyone with a basic mathematical education. It is, in its small way, a piece of writing that started something the world has not yet finished with. What Ada Lovelace had given the world, before anyone knew what to do with it, was the idea of a program. A program is a sequence of instructions for a machine, written precisely enough that the machine can follow them without ambiguity and producing a result that the writer of the program intended. The instructions can be complicated. They can include repetitions. They can include choices based on what has happened so far. They can be combined in unlimited ways. Everything in tonight's story, from this point forward, is about what people did with the idea over the next century and a half. Chapter 2. The 6 Women in the Basement. About 100 years after Ada Lovelace wrote her notes, an actual general-purpose computer was finally built. It was called ENIAC, which stood for Electronic Numerical Integrator and Computer. It was built between 1943 and 1946 at the University of Pennsylvania in Philadelphia with funding from the United States Army. It was a wartime project. The Army wanted a machine that could calculate the trajectories of artillery shells faster than the women who were doing it by hand could calculate them. The women who were doing the calculations by hand had a name. They were called computers. The word in the 1930s and 1940s did not yet mean a machine. It meant a person, almost always a woman, whose job was to perform mathematical calculations. The Army had hired about 100 of these human computers, mostly young women with college degrees in mathematics, to work in a building called the Moore School at the University of Pennsylvania. The work was slow and tedious. Each artillery shell trajectory took 30 or 40 hours of calculation by a skilled human computer. The Army needed thousands of trajectories. The work could not keep up with the war. When the Moore School engineers John Mauchly and J. Presper Eckert were funded to build ENIAC, the idea was that the machine would do the same calculations the human computers were doing, but much faster. The machine itself, when finished, was the size of a small house. It contained about 18,000 vacuum tubes, several thousand relays, and many miles of wire. It weighed 30 tons. It consumed enough electricity when running to noticeably dim the lights in the surrounding neighborhood. The machine was finished, more or less, in the fall of 1945. The war was already over by then. The Army's urgency had faded. But ENIAC was a remarkable thing, and the Moore School wanted to demonstrate it to the world. A public unveiling was planned for February of 1946. To prepare for the unveiling, the engineers needed to set the machine up to do a particular calculation that would be impressive to the journalists in attendance. The calculation was, as it happened, an artillery trajectory, since that was what the machine had been built to do. The trajectory needed to be configured on the machine. The machine, in 1945 and 1946, did not have a way to read its instructions from punched cards or any other input medium. The instructions had to be set into the machine by physically rearranging its cables and switches. The task of setting up ENIAC for the public demonstration was given to 6 women, who had been chosen from the pool of human computers because they understood the underlying mathematics well enough to translate it into the machine's operations. Their names were Kathleen McNulty, Jean Jennings, Betty Snyder, Marlon Westkoff, Frances Bilas, and Ruth Lichterman. They ranged in age from their early 20s to their late 20s. None of them had been involved in the design of the hardware. They had been told only, on being assigned, that they were to figure out how to make the machine do a particular calculation. What this involved, in practice, was a process that nobody had done before. The 6 women had to study the machine's wiring diagrams. They had to figure out, for each step of the calculation, which cables needed to be plugged into which sockets, and which switches needed to be set in which positions, so that the machine's electrical signals would flow in the right paths and the right calculations would be performed. They worked mostly in a basement room at the Moore School where ENIAC was housed, walking among the machine's panels with diagrams in their hands, climbing on ladders to reach the upper switches, tracing cables with their fingers. There was no instruction manual. There was no programming language. There was no precedent for what they were doing. They were, in retrospect, inventing the practice of programming as they went. The work took several months. By February of 1946, they had configured the machine to perform the desired calculation reliably. The public demonstration was a success. ENIAC ran the artillery trajectory in less than 30 seconds, doing in half a minute what a human computer needed 30 hours to do. At the demonstration, the press took photographs of the engineers Moakley and Eckert posing in front of the machine. The 6 women were also in the photographs, but the press releases didn't mention their names. Some of the journalists in their stories about the unveiling referred to the women in the pictures as refrigerator ladies, which was a term used at the time for fashion models who posed next to new appliances in advertisements. The women were not invited to the celebratory dinner that the engineers held afterward. The 6 women continued to work on ENIAC and on its successor machines for the next several years. They developed, during this period, what would later be recognized as the first systematic techniques for writing programs. They invented the practice of laying out a program as a flowchart before implementing it. They invented techniques for testing and debugging programs. They invented the idea of a subroutine, which is a small piece of program that could be called from many different places in a larger program, so that the same code did not have to be written twice. They wrote, in their working notes, the methods that would, decades later, become standard programming practice. What happened to them afterward varies. Betty Snyder, who later took her married name Holberton, went on to a long and distinguished career as a programmer at the National Bureau of Standards, where she worked on the design of the COBOL programming language. Jean Jennings, who took her married name Bartik, worked for several different computer companies before becoming a technical journalist. The others took various paths. Most of them, for the rest of their lives, were not particularly famous, even within the computing industry. What is striking, in retrospect, about the early history of programming is that it was largely women's work, and that this changed over the next 20 years. In the 1940s and early 50s, when computers were new and programming was considered a kind of tedious clerical task, it was given to women, in the same way that other tedious clerical tasks of the time were. As programming became more prestigious and better paid through the 1960s, the demographics of the profession shifted, and by the 1980s, programming had become predominantly male in most countries, where it has more or less remained. The 6 women who programmed ENIAC were, for several decades, mostly forgotten. They were not in textbooks. They were not in the official histories of the project. Some of them were not even named in the official photographs of the unveiling. They were rediscovered, slowly, beginning in the 1980s by a researcher named Kathy Kleiman, who had noticed the unnamed women in the old photographs and decided to find out who they were. Kleiman tracked most of them down. Several were still living. She conducted long interviews with them, made a documentary, and helped get them recognized in the histories of computing that were being written by then. By the time the last of the 6 died, in the 2010s, they had all received various honors and acknowledgments, though most of those honors came in their old age, decades after the work they had done. What the 6 women had demonstrated, more than anything, was that programming a computer was its own profession. It required its own skills, its own habits of thought, its own kinds of patience. The people who built the hardware of a computer were not the same people who made the hardware do useful work. The people who made the hardware do useful work needed to understand the hardware deeply. But they also needed to understand the problem they were trying to solve, and they needed to figure out in detail how to translate the problem into the machine's operations. This translation was a distinct skill. The 6 women in the basement at the Moore School were the first people who became expert at it. A short pause here before we continue. There's no need to keep up. The names have started to accumulate already, and they will keep accumulating, and none of them need to stay with you. If your hands have curled into anything, let them open. If you've been holding your breath even slightly, you can let it out and let the next one come slowly. The next several hours have no particular requirements. The voice keeps going whether you're tracking the story or not. Chapter 3. The Man Who Wanted to Spare His Fingers. For about the first decade of programming, every programmer worked the way the 6 women had worked. To write a program, you had to think in the machine's own language. The machine's language was a sequence of numbers, each number corresponding to one of the small operations the machine knew how to perform. Add the number in this location to the number in that location. Move this value to that location. Compare these 2 numbers, and if they are equal, jump to a different point in the program. Each of these operations had a particular numerical code, and the program was just a long sequence of such codes, handwritten by the programmer onto paper, and then punched onto cards or tape that the machine could read. The work was slow. It was also error-prone. A programmer who wrote down the wrong number, or who skipped a step, or who got confused about which location held which value, would produce a program that didn't work. Finding the mistake, once the program failed to run, was a long process of going through the sequence of codes by hand and trying to figure out which one was wrong. A typical program of the late 1940s was a few hundred lines of numerical codes. A typical programmer by the early 1950s could spend weeks or months writing and debugging a single program. There was a particular programmer at IBM in the early 1950s named John Backus who hated this. Backus, by his own later account, was an unusual person for the field. He had not been a serious student in his youth. He had been kicked out of multiple schools as a teenager. He had served in the Army during the war, working on radar equipment, and had only after the war gone back to school to study mathematics, mostly because he had noticed that he was naturally good at it. He had earned a couple of degrees at Columbia University, and IBM had hired him in 1950 to work on one of their early computers. Backus, in his first few years at IBM, did the standard work of programming in machine code. He found it tedious. More importantly, he found it inefficient. He noticed that the actual mathematical content of the calculations he was implementing was usually quite simple. The complexity of the program came almost entirely from the work of translating the mathematics into the machine's numerical codes. If you could find a way to write the mathematics directly and have the machine handle the translation, you would save an enormous amount of programmer time. The machine, after all, was much better at tedious numerical translation than any human was. The programmer should be free to think about the problem. The machine should handle the bookkeeping. In 1953, Backus proposed to his managers at IBM that he be given a small team and some time to develop what he called a translator. The translator would be a program that read programs written in a higher-level notation, something closer to the mathematics that a scientist or engineer would normally use, and produce the corresponding machine code that the computer could actually run. IBM, after some hesitation, agreed Backus was given a team of about 10 people. They started work in early 1954. The project took 3 years. Almost everyone at IBM was skeptical that it would work. The standard wisdom was that the code produced by an automated translator would be much less efficient than code written by a skilled programmer, and that no one would actually want to use a higher-level language if it cost them speed. Backus and his team had to prove the skeptics wrong. They worked over the next 3 years on making the translator produce code that was nearly as fast as handwritten machine code, while letting the programmer write in something that looked like ordinary mathematical notation. The language they developed was called Fortran, which was short for Formula Translator. In Fortran, a programmer could write a line like x equals a plus b times c, and the translator would figure out which machine instructions corresponded to that line and produce them. The programmer did not need to know which memory locations held a or b or c, or how to compute the multiplication, or where to put the result. The translator handled all of that. Fortran was released by IBM in 1957. Some of the early programmers used it, many initially refused. There was a kind of cultural divide in the late 50s between the older programmers who had learned to think in machine code and saw Fortran as a kind of cheat, and the younger ones who had not yet developed those habits and were happy to skip them. Over the next several years, Fortran gradually won. By the early 60s, most scientific programming was being done in Fortran. It became the dominant language for scientific and engineering work, and remained so for decades. Versions of Fortran are still used today, mostly in fields like weather forecasting and physics simulation, where the underlying calculations have changed less than the surrounding software industry has. What Backus had done with Fortran was establish a pattern that almost every later programming language would follow. The pattern goes like this. The programmer writes in a language designed for humans. The language has notation that looks like ordinary mathematics, or that uses words from English, or that follows some other convention that makes it readable to a person. A program called a compiler reads what the programmer wrote and translates it into the machine's own numerical instructions. The machine then runs the numerical instructions, doing the actual work. The compiler, in this arrangement, is the bridge between the human-friendly language and the machine-friendly language. This pattern of having a compiler translate between two languages is how essentially all modern programming is done. Some languages are translated all at once in a single step before the program is run. Some are translated piece by piece while the program is running. Some languages compile to other languages, which are themselves compiled to machine code. But the basic idea is the same. A human writes in a language designed for humans. A piece of software translates that language into a form the machine can execute. The programmer, freed from having to think in machine code, can think about the problem. Backus, after Fortran, continued to do influential work for several more decades. He worked on the design of later programming languages. He invented a notation called Backus Norform for describing the grammar of programming languages, which is still used today by language designers. He published an influential paper in 1977 arguing that the dominant style of programming, which he had himself helped popularize with Fortran, was actually limiting, and that programmers should think about their work differently. The paper, which was the speech he gave when he received the Turing Award, was titled, "Can Programming Be Liberated from the von Neumann Style?" It was characteristic of Backus that he had won the highest honor in his field and then used the occasion to argue that the field needed to be reorganized. Backus died in 2007 at the age of 82. The languages that were direct descendants of Fortran were already, by that point, less dominant than they had been. But the pattern he had established of writing in a higher-level language and having a compiler do the translation had become so universal that nobody, by the time he died, was writing programs any other way. Chapter 4. The Function. The story of programming after Fortran branched in many directions. Different languages were developed in different places for different purposes. Some were for scientific work, some for business, some for teaching, some for handling text, some for controlling industrial machines. Each language had its own personality. Each language emphasized different ideas about how programs should be organized. The most important idea, the one that nearly every language eventually adopted, was something that came from a researcher named John McCarthy, who in 1958 was a young professor at the Massachusetts Institute of Technology. McCarthy had recently coined the term artificial intelligence in connection with a workshop he had organized at Dartmouth College in 1956, and he was thinking about how computers might be made to do tasks that required something more than mathematical calculation. He wanted them to do reasoning. He wanted them to handle language. He wanted them, eventually, to think. The language he came up with in 1958 and 1959 was called Lisp, which was short for Lisp processor. Lisp, in its earliest form, was unlike anything that had been built before. It was based on a piece of mathematical logic developed in the 1930s by a logician named Alonzo Church, called the lambda calculus. The lambda calculus was, in essence, a precise mathematical description of what a function was. McCarthy took this description and turned it into the basic building block of a programming language. To understand what McCarthy did, it helps to spend a few minutes on the idea of a function. A function, in the sense McCarthy meant it, is a small piece of code that takes some input and produces some output. You can think of it as a kind of machine inside the machine. A small box. You put something in one side, something comes out the other side. The function decides, based on what was put in, what comes out. A function might be very simple. A function to double a number takes one number as input and returns twice that number as output. A function to add two numbers takes two numbers as input and returns their sum. A function to find the longer of two words takes two words as input and returns whichever one has more letters in it. The function does one specific thing. It does it the same way every time. You can use it again and again on different inputs. What McCarthy realized was that you could build entire programs out of functions. A big function could be made by combining smaller functions. A function to calculate the average of a list of numbers could be built by combining a function to add the numbers together with a function to count how many there were and a function to divide one number by another. Each small function did one thing. The combination of small functions did something bigger. This style of programming, of breaking a complicated task into small functions and then combining them, became one of the basic ways that programmers organize their work. It still is. A modern programmer working on almost any kind of project spends much of their time deciding which functions to write, what each function should take in and what each one should produce, and how the functions should fit together. The functions become the small, reusable parts. A program, looked at from a certain angle, is a tree of functions calling other functions, calling still smaller functions, all the way down to the operations the machine itself can perform. Lisp had several other features that were unusual for its time and that later languages would adopt. One of the most important was something called recursion. Recursion is when a function calls itself. This sounds, at first, like it would cause an infinite loop, but it doesn't, as long as the function knows when to stop. The simplest example is the factorial function, which calculates the product of all the whole numbers from 1 up to a given number. The factorial of 5 is 5 times 4 times 3 times 2 times 1, which is 120. You can compute factorials with recursion by writing a function that, when given a number, calls itself with the next smaller number and multiplies the result. The function stops calling itself when it gets down to 1. The whole calculation unfolds in a kind of cascade, each level calling the next until the base case is reached and the answers travel back up. Recursion is a way of thinking about problems that took a while for programmers to get used to. It can be confusing the first few times you encounter it. But it turns out to be enormously useful for certain kinds of problems, especially problems that involve trees of data or paths through networks or any kind of structure that contains smaller versions of itself. Most modern programming languages support recursion. Most working programmers use it routinely. The fact that it works, and that programs can call themselves in this kind of unfolding way, is one of those small surprises in the structure of mathematics that turns out to be unexpectedly useful for practical work. Another feature of Lisp, which has since been picked up by many other languages, was something called automatic memory management. In most early programming languages, the programmer was responsible for keeping track of which areas of memory the program was using, and for releasing those areas when they were no longer needed. This was tedious and error-prone. A programmer who forgot to release some memory would cause the program to slowly run out of memory and eventually crash, an error called a memory leak. A programmer who released memory that was still in use would cause the program to corrupt itself. Lisp, instead of putting this burden on the programmer, included a piece of code built into the language that automatically tracked which memory was still in use and which was free to reuse. The piece of code was called a garbage collector, because its job was to clean up memory that the program was no longer using. The garbage collector ran in the background periodically and freed up memory that wasn't being used anywhere. The programmer didn't have to think about it. The programmer could focus on the actual problem. Automatic memory management is now standard in most modern programming languages. Java has it, Python has it, JavaScript has it, Ruby has it. The languages that don't have it, like C and C++, are mostly used in situations where the programmer needs very precise control over the machine's behavior, like operating systems or embedded devices. For most programming, the garbage collector that Lisp introduced in 1958 is now invisible and universal. Lisp itself, the original language, never became one of the mainstream programming languages. It had a small but devoted following throughout the second half of the 20th century, particularly in the artificial intelligence research community and in the programmable text editor Emacs, which was written in a variant of Lisp and which is still used by some programmers today. The ideas of Lisp, however, the central role of functions, the use of recursion, automatic memory management, spread to almost every other language, until by the 2010s essentially every popular programming language had absorbed them. McCarthy himself spent most of his career at Stanford, where he founded the Stanford Artificial Intelligence Laboratory in 1963. The laboratory, which was eventually housed in a building in the hills above the Stanford campus, was by all accounts one of the more unusual research environments in the United States in the 1960s and 70s. McCarthy had a relaxed attitude toward how his researchers spent their time. The lab had a sauna. It had a vending machine that students could refill themselves on the honor system. Researchers came in at strange hours. The culture was deliberately loose, on the theory that creative work was more likely to happen in an environment that didn't enforce rigid schedules. What came out of the laboratory over the decades included a great deal of foundational work on artificial intelligence, robotics, computer vision, and language understanding. Many of the researchers who passed through the laboratory in the 60s and 70s went on to lead other research programs around the world. McCarthy himself worked on a wide range of topics, including some that were ahead of their time. He proposed, in 1961, that computer time could be sold as a utility, the way electricity is sold, with users paying only for the time they used. The idea, which he called time-sharing, took several decades to be commercially realized in the form we now call cloud computing. He worked on artificial intelligence research for the rest of his life. He never saw the systems he hoped to build come into existence in his lifetime, but he laid much of the groundwork that later researchers built on. He died in 2011 at the age of 84. The languages that were most directly derived from his work, including Lisp variants like Scheme and Clojure, are still used by small communities of programmers, and the ideas he introduced are used by everyone. What McCarthy had given the world, more than the language itself, was the centrality of the function as the basic unit of programming. The idea that a complicated task can be broken into small pieces, each of which does one thing, each of which can be tested separately, each of which can be combined with other pieces in flexible ways. This idea is now so deeply built into how programmers think that almost no one notices it. It is what programming feels like, from the inside. You have a big problem. You break it into smaller problems. You write a function for each smaller problem. You combine the functions. The big problem, somehow, gets solved. Chapter 5, The Dutchman Who Got Angry. Up to this point, we have mostly been talking about pieces of programs, functions and instructions and lines of code. But a program is not just a collection of pieces. A program is also a sequence. The pieces have to be executed in a particular order. The order has to be chosen carefully, because what the program does depends on which instructions run, in which order, and how many times. There are, fundamentally, 3 ways that a program can control the order of its own execution. They are simple enough that you can hold all 3 in your head at once. The first is sequence, which is just doing one thing after another. Do step 1. Then do step 2. Then do step 3. The second is selection, which is choosing between alternatives based on some condition. If this is true, do step A, otherwise do step B. The third is iteration, which is doing something repeatedly until some condition tells you to stop. Do step A again and again until you've done it 10 times, or until the number you're working with is small enough, or until you've reached the end of the list. These 3 patterns, taken together, are enough to build any program of any complexity. Anything a computer can compute can be expressed using only sequence, selection, and iteration. This fact was proven in 1966 by 2 Italian computer scientists named Corrado Biem and Giuseppe Jacopini, in a paper that has since become one of the foundational theorems of structured programming. The reason this fact matters, even though it sounds technical, is that there had been, before 1966, a quite different way that programmers had been thinking about controlling the order of execution. The earlier way involved a programming instruction called goto. Goto was, as the name suggests, a command that told the program to jump to a different point in its own code. A program might say, at this point, goto line 47. The program would then resume executing from line 47, ignoring whatever came after the goto in the original sequence. Goto was, in its early days, considered a perfectly normal way to write programs. The early machine code instructions had something like it. Fortran had it. Many of the early languages had it. Programmers used it to handle all kinds of situations that didn't fit cleanly into the simple sequence and loop patterns of structured programming. Goto was flexible. You could use it to do almost anything. But Goto had a problem, which became increasingly apparent as programs got larger. The problem was that, when you read a program that used Goto, you couldn't easily follow what the program was doing. The control could jump anywhere. A line of code might be reached from many different places in many different states. To understand what would happen at any particular point in the program, you might have to trace through every possible path the program could have taken to get there. For small programs, this was manageable. For large programs, it became, in practice, impossible. The programs were said to look like spaghetti, with control lines crossing every which way. In March of 1968, a Dutch computer scientist named Edgar Dijkstra wrote a short letter to the journal Communications of the AM, which was the main professional journal of the computing field. The letter was titled "Go-To Statement Considered Harmful." It was about 3 pages long. It argued that the Goto statement should be eliminated from higher-level programming languages, and that programs should be written using only the 3 structured control patterns of sequence, selection, and iteration. Dijkstra's argument was straightforward. He pointed out that when programs are restricted to structured control patterns, you can understand each piece of the program by reading it from top to bottom, without having to trace through arbitrary jumps. Each loop is a self-contained unit. Each branching choice has a clear set of alternatives. The program's structure mirrors the structure of the problem it solves, instead of being a tangle of jumps. The programs are easier to read, easier to debug, and easier to modify by someone other than the original author. The letter, when it was published, caused a remarkable amount of controversy. Many older programmers found Dijkstra's argument annoying, or arrogant, or simply wrong. They had been writing programs with Goto for years. They knew how to do it. They didn't want to be told they had been doing it wrong. The letter, by some accounts, started arguments at programming conferences for years afterward. Dijkstra was, by his own preferences and by the accounts of people who knew him, an unusually opinionated man. He was tall, thin, and Dutch. He had been born in 1930 in Rotterdam. He had studied mathematics and physics at the University of Leiden. He had become interested in programming in the early 1950s, when computers were just starting to be available in European universities. He had developed a reputation, by the mid-60s, for writing extremely clear and precise papers, and for being willing to say in print that other people's work was wrong. He was also, somewhat eccentrically for his time, a believer that programs should be thought about with the same precision that mathematicians applied to proofs. A program, in Dijkstra's view, was a kind of mathematical object. It should be designed carefully, in advance, with proofs that it would work correctly under all conditions. The actual coding should come last after the design was already verified by reasoning. The casual, exploratory, learn-as-you-go approach that many programmers took to writing code seemed to him to be unprofessional and dangerous. Dijkstra had several other personal habits that made him a memorable figure among the people who knew him. He refused, for most of his career, to use a computer himself. He believed that the activity of programming should be done with pen and paper, where you could think clearly, and that the actual machine should only be involved at the very end to verify what you had already worked out. He wrote his papers by hand in a beautiful and deliberate cursive that he had developed over many years, on numbered sheets of paper that he then photocopied and distributed to his correspondents around the world. The papers came to be known as EWDs after his initials. There are over 1,300 EWDs in total, written between the 1960s and his death. They cover every conceivable topic in computer science and many topics outside it. They are all available, scanned on a website maintained by the University of Texas at Austin, where Dijkstra spent the last 2 decades of his career. Any programmer in the world today can read his handwritten thoughts on whatever topic interested him at whatever moment. He also had a habit of writing strongly opinionated remarks about other people's work, which he expected to be received as professional criticism, but which were often taken as personal attacks. He thought, for example, that the basic programming language, which was widely taught to beginners in the 1970s and 80s, was so badly designed that anyone who learned it would have their mind permanently damaged for serious programming. He thought that the field of software engineering, which had grown up around the work of people like Margaret Hamilton at MIT, was a mistake, because the activity should be considered a branch of mathematics rather than a branch of engineering. Many of his views were minority views even within computer science. He held them all firmly, in print, in his handwritten EWDs, for decades. The argument about Goto, in the years after Dijkstra's letter, was eventually won by the structured programming side. The languages designed in the 1970s and 80s, including Pascal and C and many others, were designed around structured control patterns. The use of Goto declined sharply. By the 1990s, Goto was either absent from most popular languages or strongly discouraged in the ones that still had it. Modern programmers, with very few exceptions, write programs using only sequence, selection, and iteration. The structured programming revolution that Dijkstra started in his 1968 letter is, in some sense, complete. Dijkstra himself continued, for the rest of his career, to argue for a particular kind of programming culture. He thought that programming should be taught more rigorously, with more attention to mathematical reasoning. He thought that programmers should be expected to prove that their programs were correct before running them, instead of just running them and seeing what happened. He thought that the casual culture of modern programming, where programmers wrote a little, tested a little, fixed bugs, and iterated, was an embarrassment to the field. His views on this never quite won. The casual, iterative culture of programming has, if anything, become more dominant since his time. Most programmers today write programs the way Dijkstra would have considered amateurish, by trying things, seeing what happens, fixing what breaks, and gradually homing in on something that works. The work goes faster this way, and for most kinds of software it is good enough, even if it is not the rigorous engineering Dijkstra wanted. But Dijkstra's smaller, more specific argument about Goto did win. Modern programs do use the 3 structured patterns. Programmers do think about their code in terms of loops and branches and sequences, rather than in terms of arbitrary jumps. The result is that programs today are more readable than they would otherwise be. A programmer can pick up someone else's code, read it from top to bottom, and have a reasonable chance of understanding what it does. This was much less true in the years before 1968. It is, in a small but real way, one of the gifts of Dijkstra's letter. He died in 2002, at the age of 72. His handwritten papers, called EWDs after his initials, are archived online and run to over 1,000 documents on every conceivable topic in computer science, all written in his careful and exacting style. Many of them are about programming. A few of them, even now, are about the Goto statement and how he had been right about it. Something around the middle of the story, now, the exact spot doesn't matter. If parts of what we've already gone through have already faded, that's the right thing for this hour. The voice is going to keep its same slow pace through the second half. Nothing in the chapters ahead is more important than the chapters behind. Let your face soften if it's tightened. Let one breath go a little longer than the last one if it wants to. We're walking, not running. We have a long way still to go, and we have all the time we could need. Chapter 6. Small Things That Know How to Do Things. So far, we have talked about programs as collections of functions and as sequences of control structures. But there is another way of thinking about programs, which became popular in the 1970s and which is now the way most large programs are organized. The way is called object-oriented programming, and the person most associated with its invention is a researcher named Alan Kay, who at the time was working at the Xerox Palo Alto Research Center in California. Kay had grown up in Massachusetts, served in the Air Force, and earned a doctorate in computer science from the University of Utah in 1969. He had moved to Palo Alto in 1970 when Xerox opened its new research lab there, and had spent the early 70s working on a series of related projects that all came back to the same vision. The vision was that computers should be tools that people, including children, could use to think with. He had imagined, in a paper he wrote in 1972, a small portable computer he called the Dynabook, which would be powerful enough to do anything a child wanted, and would be programmable in a way that made the activity of programming itself approachable to non-experts. To make programming approachable, Kay believed, you had to change the way people thought about it. The dominant style of programming in the early 70s was what Kay called procedural, the style we have been talking about, in which a program is a sequence of instructions, organized into functions that operate on data. The data was passive. The instructions were active. The instructions read the data, transformed it, and produced new data. The programmer, when writing a program, had to keep careful track of which data was where, and which instructions would touch it, and what state the data would be in at each step. Kay's alternative was to think about programs in a different way. Instead of separating data from instructions, you would bundle them together. You would have small entities which Kay called objects, each one containing both some data and the instructions for operating on that data. An object representing a circle would know its own radius and its own position on the screen, and would also know how to draw itself, how to move itself, how to grow or shrink itself. An object representing a person in a simulation would know its own name and age and weight, and would also know how to eat, how to sleep, how to greet other people. Programs in this style would not be sequences of instructions operating on data. They would be communities of objects, sending each other messages. If one object wanted another to do something, it would send the other a message asking for it. The receiving object would decide, based on its own internal rules, how to respond. The objects would communicate, like little citizens of a small society, and the work of the program would emerge from their interactions. This was, when Kay first started talking about it, a strange way of thinking. most programmers were not used to it. But it had certain advantages. It encouraged programmers to think about their problems in terms that were closer to the way humans normally think about the world. The real world is full of things that have properties and that can do things. A car has a color and a speed and a number of wheels, and it can accelerate and turn and brake. A book has a title and an author and a number of pages, and it can be opened and read and put away. Most domains that programmers wanted to model, bank accounts, library catalogs, video games, simulations of biological systems, were full of objects with properties and behaviors. Organizing the program around objects, rather than around procedures, made the program more like the thing it was supposed to model. Kay and his small team at Xerox PARC implemented this style of programming in a language they called Smalltalk. Smalltalk was developed in several versions during the 1970s. The final version, Smalltalk 80, released in 1980, was the first complete and influential object-oriented programming language. It was also, by the standards of the time, a remarkably elegant language. Everything in Smalltalk was an object. Numbers were objects. Letters were objects. The program itself was made of objects. Even the things that, in other languages, would be considered control structures like loops and branches were implemented as messages sent to objects in Smalltalk. Smalltalk also had a feature that was unusual for its time, and that has not always been preserved in later languages. The Smalltalk environment was alive while the program ran. You could pause a running program, examine the state of any object, change the code of any object, and resume the program with the new code in place. There was no separate compile and run cycle. The program and the development environment were the same thing. You could, in some real sense, build the program by talking to it while it was running. The ideas of Smalltalk spread gradually over the following decades. The next major object-oriented language was C++, designed by a researcher at Bell Labs named Bjarne Stroustrup in the early 1980s. C++ took the ideas of objects from Smalltalk and combined them with the speed and low-level control of the older C language. C++ became one of the most widely used programming languages of the late 20th century, particularly for system software, video games, and large applications. After C++ came Java, designed by a small team at Sun Microsystems in the early 1990s. Java took the object-oriented ideas of C++ and combined them with automatic memory management, like Lisp had introduced 35 years earlier, and with a design that allowed Java programs to run on many different kinds of computers without needing to be recompiled. Java became enormously popular in the late 90s and the 2000s, particularly for business software and Android phone applications. After Java came many other object-oriented languages. Python, designed in 1991 by a Dutch programmer named Guido van Rossum, is object-oriented at its core. Ruby, designed in the mid-90s by a Japanese programmer named Yukihiro Matsumoto, is heavily object-oriented. JavaScript, the language that runs in every web browser, supports objects in its own particular way. Almost every major modern programming language has objects somewhere in its design. What Alan Kay had given the world with Smalltalk was a way of organizing programs that has dominated software development for the last 40 years. The idea that programs should be communities of small things that bundle data with behavior, that send each other messages to get things done, that can be examined and modified while the program is running. These ideas now shape almost every large software project in existence. The phone in your pocket, the website you are reading, the application you wrote your last email in are all organized internally around objects. The objects are mostly invisible to you. They are the small machinery, the unnamed citizens of the program's small society. Kay himself, like several of the people in our story, has spent the years after his most influential work continuing to work on the same broad problem. He has continued to argue, in lectures and papers, that programming is still not approachable enough to ordinary people, and that the field has gotten stuck in approaches that are less elegant than what was possible in the 1970s. He is famous in the small community that pays attention to such things, for the statement that the best way to predict the future is to invent it. He has spent his life trying to invent it. He is, as of these recordings, still alive, in his 80s. Chapter 7. The Woman Who Saved the Moon Landing. Programs, no matter how carefully written, almost always contain mistakes. A mistake in a program is called a bug. The word is older than computers. It was used in the late 19th century to refer to any small defect in a piece of machinery. The term was carried over to computers in the 1940s, when computers started to have small defects that needed fixing. A bug can be many things. It can be a typo where the programmer typed the wrong character and didn't notice. It can be a wrong number, where the programmer intended to write a 5 and wrote a 6. It can be a logic error where the programmer thought through the problem incorrectly and wrote code that does the wrong thing in some specific situation. It can be a misunderstanding, where the programmer thought a certain piece of code did one thing when it actually did another. It can be a missing case, where the programmer wrote code for the situations they thought of and forgot to write code for some situation they didn't think of. The work of finding and fixing bugs is called debugging. Debugging is, for most professional programmers, the single largest category of activity in their daily work. Programmers spend more time, on the whole, debugging existing code than they do writing new code. The skill of programming is, in some real sense, the skill of being patient with one's own mistakes. The story of the most famous debugging incident in the history of programming belongs to a woman named Margaret Hamilton, who in 1969 was 33 years old and was running the software engineering team at the MIT Instrumentation Laboratory. The Instrumentation Laboratory was the place that had been contracted by NASA to build the guidance computer for the Apollo spacecraft, which were about to attempt to land humans on the moon. Hamilton had grown up in Indiana, studied mathematics at Earlham College, married another mathematician named James Hamilton, and had a daughter, Lauren, in 1959. Shortly after the daughter's birth, James Hamilton enrolled in Harvard Law School. To support the family, Margaret took a job at MIT, where she had originally planned to work for a few years and then go to graduate school herself. She never did go. She stayed at MIT, and her career in computing, which she had not particularly planned for, expanded to fill the rest of her professional life. By 1964, she had moved to the instrumentation laboratory and joined the Apollo program. The program was by then ramping up to its full intensity. NASA had committed to landing humans on the moon by the end of the decade. The guidance computer was one of the most demanding pieces of the project. It would have to navigate the spacecraft through space, control its rockets during landings and takeoffs, and respond in real time to whatever situations arose during the missions. The computer was small. By even the standards of 1964, it had only about 4 kilobytes of memory. And the software had to be extraordinarily efficient and extraordinarily reliable. Any failure of the software in flight could kill the astronauts. Hamilton, by the mid-60s, had become the leader of the team responsible for the Apollo flight software. She had a particular set of concerns that, by the accounts of her colleagues, were unusual for the time. She thought that programmers needed to take their work more seriously as a profession. She thought that the activity of writing software was, in fact, an engineering discipline, no less rigorous than the design of bridges or aircraft, and that it deserved to be treated as such. She coined, in the late 60s, the term software engineering to describe what her team was doing. The term was at first somewhat ridiculed by other engineers who did not consider software a real engineering field. By the 1980s, it had become the standard name for the profession. There is a particular story from this period that is worth telling carefully, because it gives a sense of what debugging actually involves. In the year or so before Apollo 11, while Hamilton was working long hours on the software, she sometimes brought her daughter Lauren to the laboratory with her. Lauren, who was about 4 years old at the time, would amuse herself by playing with the Apollo simulator while her mother worked. The simulator was a copy of the actual flight computer used for testing the software in conditions that mimicked an actual mission. One day, Lauren, by accidentally pressing a particular sequence of buttons on the simulator, caused the program to crash. Specifically, she had selected, in the middle of a simulated landing, a program called P01, which was the pre-launch initialization routine. P01 was meant to be run only before launch, on the ground, when the spacecraft was still on Earth. Running it during a landing erased the navigation data that the computer was using to track the spacecraft's position, which caused the simulated mission to fail. Hamilton, watching this happen, realized that it was, in principle, possible for an astronaut to make the same mistake during an actual mission. She proposed to her superiors that the software be modified to prevent it. Specifically, she wanted to add a check that would refuse to run P01 once the mission had started. Her superiors said no. The astronauts, they pointed out, were among the most extensively trained pilots in the world. They would not make a 4-year-old's mistake. Adding extra code to defend against such mistakes would waste precious memory that the small computer could not spare. Hamilton, by her own later account, accepted the decision but documented in writing that it was, in her view, the wrong call. She added a sentence to the program's documentation, noting that P01 should not be selected during a mission. A few months later, during Apollo 8, which was the second crewed Apollo mission and the first to orbit the Moon, an astronaut named Jim Lovell accidentally selected PO1 during the mission, more or less the way Lauren had done in the simulator. The mistake erased the navigation data. The mission was nearly lost. The ground crew, after some hours of frantic work, was able to transmit corrected navigation data back to the spacecraft and recover the mission. Hamilton, when she heard about what had happened, was quietly vindicated, although she did not, by the accounts of her colleagues, dwell on it. The more famous moment in Hamilton's career came during Apollo 11 in July of 1969, during the final descent to the lunar surface. The spacecraft was about to make the actual landing. The lunar module was being controlled by Neil Armstrong and Buzz Aldrin, but most of the navigation was being handled by the small guidance computer. About 1,000 meters above the surface, the computer started flashing error codes on its display. The codes were 1202, and then, a few seconds later, 1201. The codes meant, in the language of the computer, that the computer was being asked to do more work than it could handle. Tasks were being requested faster than the computer could complete them. The computer was, in effect, overloaded. Hamilton's software had been designed for this exact situation. The software included what was called a priority display system, which was a feature that, when the computer became overloaded, would automatically drop lower priority tasks and continue executing the more important ones. The landing critical tasks, the ones that kept the spacecraft on track for the lunar surface, had been assigned high priority by Hamilton's team. The less critical tasks, like updating certain status displays, had been assigned lower priority. When the 1202 alarm fired, the computer kept executing the landing tasks and dropped some of the lower priority work. The astronauts, on the ground crew's advice, continued the landing. What had caused the overload was a small hardware issue with one of the spacecraft's radar systems, which was sending the computer more data than it had been expected to send. The computer, faced with this unexpected flood of data, would have failed catastrophically without Hamilton's overload handling code. It would have either crashed completely, requiring an abort of the landing, or it would have started executing all the tasks at slower than real-time speeds, missing critical timing windows for the descent. Either failure would have ended the mission and possibly the astronauts' lives. Hamilton's careful design, which had been done years earlier and tested through long hours of simulator work, was what kept the landing on track. A few minutes after the alarm started, Armstrong landed the lunar module on the surface of the Moon. Hamilton, who was watching the landing from MIT, did not, by her later account, fully realize at the time how much depended on what her team had built. She was 33 years old. She had a young daughter at home. She had been working on the project for 5 years. The landing happened. The astronauts walked on the Moon. The mission was a success. Her work, which had been substantial but had not been particularly celebrated by NASA, became famous later, partly through the persistent storytelling efforts of people like Lauren Hamilton, who as an adult became a software developer herself and worked to make sure her mother's contributions were remembered. There is a particular photograph of Margaret Hamilton from this period that has, in the years since, become one of the more widely shared images in the history of computing. The photograph was taken at MIT sometime in 1969 or 1970 by a MIT photographer. It shows Hamilton in her early 30s standing next to a stack of paper that comes up roughly to her shoulder. The stack is composed of the printouts of the source code that her team had written for the Apollo program. The stack is taller than she is, and she is standing next to it with a small, slightly amused expression, as if she is not quite sure what to do with this much paper. The photograph has been used in many different contexts to make many different points. Some people use it to make a point about how complicated the Apollo software was. Some people use it to make a point about how women were doing this kind of work long before they were credited for it. Some people use it just because it is a striking image. The photograph, like the work it represents, sat in MIT's archives for decades before becoming widely known. Margaret Hamilton received the Presidential Medal of Freedom in 2016, 47 years after the moon landing. She was, by then, in her late 70s. She continued, in interviews she gave around the time of the medal, to talk about the importance of treating software seriously as an engineering discipline, and about the importance of designing systems that handle unexpected situations gracefully. The work of programming, in her view, was not just about getting code to work in the normal case. It was about thinking through, with great patience, all the unusual cases that could happen, and making sure the program would behave well in each one. This is, in some real sense, the deepest skill of programming. The skill is not the writing of code. The skill is the imagining of everything that could possibly go wrong, and the writing of code that does the right thing in each case. A great programmer, in this view, is someone who can hold 100 edge cases in their head at once and not be overwhelmed by them, but instead work through them one by one, with the patience of someone who knows that somewhere a 4-year-old is going to press the wrong button at the wrong moment, and the software had better be ready for it. The story is moving into its later chapters now, and the energy is going to come down with them. There's nothing in what's coming that you need to grip onto. The technical pieces will keep getting introduced, and they'll keep being explained slowly, and you can let them pass by you without trying to gather them up. The voice will stay the same. The night will stay the same. Wherever you happen to be, in your own particular bed, the story can keep going around you while you do whatever you're going to do. Chapter 8. The 11 lines that broke a small part of the internet there is something about modern programming that would have astonished any of the programmers we have talked about so far. The thing is the sheer amount of code that any given program now contains that was written by someone other than the program's author. A typical modern application, a website, a phone app, a desktop program, is built using code from dozens or hundreds of other programmers. The other programmers, in most cases, the author has never met. The code, in most cases, the author has never read. The application works because the author has written a small piece of original code, and has invoked from that small piece large pieces of pre-existing code that other people wrote, and the pre-existing code, when invoked, does most of the actual work. The pre-existing code is organized into things called libraries, or sometimes packages. A library is essentially a bundle of code that someone wrote and made available for other programmers to use. The library does some specific thing. It might handle the work of reading from a particular kind of database. It might handle the work of decoding a particular kind of image file. It might handle the work of formatting dates for display. The author of the library has done the work once and made the result available, so that other programmers do not have to do the same work again. This pattern of programmers reusing each other's code has grown enormously over the last few decades. In the early days of programming in the 1950s and 60s, programmers mostly wrote their own code from scratch. Each program was its own little island. By the 1970s, libraries had become more common, but they were usually shared informally between colleagues at the same institution. By the 1990s, with the rise of the Internet, programmers had started to share libraries publicly. By the 2000s, there were large central registries called package managers where any programmer could publish a library and any other programmer could download it. The result, by the 2010s, was a programming culture in which writing a new application was usually a matter of combining many libraries that someone else had already written. A typical modern application might depend on 100 or 200 libraries. Each of those libraries might depend on 100 or 200 other libraries. The full graph of dependencies for a modern application can include thousands of libraries, contributed by thousands of programmers, most of whom have never met, working in dozens of different countries. This arrangement has obvious advantages. It lets a single programmer working alone produce applications that would have taken a team of hundreds of programmers to build a few decades ago. It encourages specialization. The person who writes the date formatting library can become very good at date formatting. The people who use the library don't need to learn the details of date formatting. They can just call the library and trust it to do the work. Everyone benefits. The arrangement also has some disadvantages which only become visible in unusual situations. One of the most famous of those situations occurred on March 22, 2016, and it involved a piece of code that was 11 lines long. The programmer who wrote the 11 lines was named Azer Kulu. He was Turkish, in his early 30s, living in Istanbul. He had been an active contributor to the world of JavaScript programming, which was the language used in web browsers. Over the years, he had written and published on a public package registry called NPM several hundred small libraries. Most of them were small utilities, the kind of thing that did one simple task that programmers needed to do over and over. One of his libraries, called leftpad, was a function that took a piece of text and added spaces or other characters to its left side so that the text would line up to a particular width. The library was 11 lines long. It was used by, among many other libraries, several extremely popular ones, including some that were used in the build systems of major websites and applications. In early 2016, Kulu was contacted by a company called Kik Interactive, which made a messaging application called Kik. Kik Interactive's lawyers had noticed that Kulu had published a small library on NPM called Kik, which he had named after a personal nickname. Kik Interactive wanted him to give up the name. Kulu refused. The lawyers contacted NPM directly. The NPM staff, after some deliberation, sided with the company. They transferred the name Kik from Kulu's control to Kik Interactive's control, against Kulu's wishes. Kulu was furious. He felt that NPM had violated its own principles by taking a name away from one of its contributors at the request of a corporation. He decided, in protest, to unpublish all of his packages from NPM. He clicked the Unpublish button again and again several hundred times, until all of his libraries had been removed from the registry. Then he posted on a blog an explanation of what he had done. One of the libraries he had unpublished was LeftPad, the 11-line text padding function. LeftPad was, although Kulu probably did not fully realize it at the moment he unpublished it, one of the most depended upon packages in the NPM ecosystem. It was used directly by some popular libraries. It was used indirectly through chains of dependencies by many more. When Kulu unpublished it, every program that had been depending on it suddenly could no longer be built. The build process, when it tried to download LeftPad, got an error saying the package no longer existed. The effects over the next several hours were widespread. Programmers around the world found that their applications were no longer building. Major companies had problems. Facebook had problems. Spotify had problems. Netflix had problems. The 11 lines of code that had vanished from NPM were suddenly conspicuously missing from a substantial fraction of the world's software infrastructure. NPM staff, watching the chaos, made a decision that had no precedent. They restored LeftPad to the registry without Kulu's permission. They argued in a public statement that the situation was unusual enough that they had to act for the good of the broader community. Kulu, of course, was furious about this too. He had not given permission. The package was his work. But the package was also depended on by so many other people that it had become, in a sense, public infrastructure. The decision was controversial. It was also, in the moment, effective. The world's build systems started working again. The whole incident, which came to be known as LeftPadgate, became, in the years afterward, the canonical example of a particular kind of fragility in modern software. The fragility is that a single programmer, anywhere in the world, can have an enormous impact on the rest of the programming ecosystem by deciding to remove a small piece of code. The programmer might be doing it for a reason that has nothing to do with anyone else. They might be doing it in a moment of pique, the way Kulu did. They might be doing it because they're getting out of programming and don't want to maintain their old work anymore. They might be doing it because they died, and no one is taking over their packages. The other thing the incident illustrated was how interconnected the modern programming ecosystem had become. Most programmers before March of 2016 would not have known that LeftPad existed. Almost no programmer had read its 11 lines of code. But most programmers, it turned out, were using it, indirectly, in some chain of dependencies that ran from their application through dozens of other libraries before reaching the small text padding function at the bottom. The dependencies were invisible. The dependencies were also, as it turned out, surprisingly important. The modern programming culture, built on small reusable libraries that programmers shared with each other, was an enormous productivity boost. It was also, when you looked at it carefully, full of small, fragile pieces that almost nobody knew about, holding up much larger structures that almost nobody had bothered to inspect. The lessons of LeftPadgate were absorbed, slowly over the following years. The NPM registry made it harder for programmers to unpublish packages that other people were depending on. The broader community started paying more attention to which small packages they were depending on, and on who was maintaining them. There are now, as of these recordings, occasional conversations among programmers about the importance of paying the maintainers of widely used small libraries, who often work for free and receive little recognition for keeping critical pieces of infrastructure running. The conversations have not, on the whole, led to dramatic changes. The system is still mostly held together by small volunteer effort. The fragility is still there. It works mostly because the people who maintain the small pieces are, on the whole, conscientious. When one of them is not conscientious, or when one of them has a bad week, the consequences can be larger than anyone would have expected. There is another famous story, 2 years earlier than Left Pad, that illustrates a different version of the same fragility. In April of 2014, a security researcher discovered a serious bug in a piece of software called OpenSSL, which was the library that handled the encryption used by most websites on the Internet. The bug, which came to be called Heartbleed, would let attackers read small pieces of data from the memory of any server running OpenSSL, including passwords, private keys, and other sensitive information. The bug had been in the OpenSSL code since 2012, 2 years earlier, where it had been introduced by a small mistake in a routine update. The thing that made the Heartbleed incident particularly striking, as a story about how the modern software ecosystem worked, was who had been maintaining OpenSSL. The library, which was used by something like 2/3 of all the secure websites on the Internet, was being maintained, in 2014, by a tiny group of volunteers. The total annual funding for OpenSSL was about $2,000 in donations. Only one person, a German programmer named Stephen Henson, worked on it full-time, and he did so without a salary. The piece of software that protected the world's banking websites, e-commerce sites, government sites, and almost every other secure service on the Internet was, in some real sense, a small open-source project maintained by people in their spare time, on a shoestring budget, with no real institutional support behind it. After Heartbleed, there was, briefly, a great deal of attention paid to the problem of how critical open-source software was funded. A coalition of large technology companies set up a fund called the Core Infrastructure Initiative, which provided money to support the maintainers of essential libraries like OpenSSL. The funding helped, but the broader problem of the modern software ecosystem being held together by a vast web of small libraries maintained by people without much support remained. It is still, more or less, the structure of the system today. What modern programming has become, in some real sense, is a collaborative activity at a global scale. The programmer who sits down to write an application is, even when working alone, working with hundreds or thousands of other programmers, most of them dead or asleep or in some other country, all of whose past work is being assembled and reassembled in the application as it is built. The activity is solitary, but it is also profoundly collective. The 11 lines of code that Kulu wrote in a single afternoon ended up holding up a small but real piece of the entire Internet, until, briefly, in March of 2016, they didn't. Chapter 9. A Weekend in Linus Torvalds' Kitchen. Programmers do not just write code. They also keep track of code. When a programmer changes a program, they need to be able to remember what the program was before the change, in case the change turns out to be wrong and needs to be undone. When several programmers work on the same program at the same time, they need a way to combine each other's changes without losing anyone's work. When a program has been in development for years, they need a way to look back at any moment in its history and see what the code looked like then. The tool that handles all of this is called version control. A version control system, when it works well, is a kind of time machine for code. It records every change that any programmer makes to the project. It lets you see the project as it was last week, or last month, or last year. It lets you compare two versions and see what changed between them. It lets you merge changes from different programmers together, even if they were working on the same file at the same time. It is one of the most important pieces of software in the modern programmer's daily life. Most programmers spend, on the average day, almost as much time interacting with the version control system as they spend writing actual code. The version control system that almost every modern programmer uses in the 2020s is a system called Git. Git was created by Linus Torvalds, who is the Finnish programmer who created the Linux operating system in 1991 and who, by the early 2000s, was the most well-known open-source programmer in the world. We met him briefly in an earlier story tonight. He was, by then, in his mid-30s, living in Oregon with his family, and spending most of his time coordinating the development of the Linux kernel, which was being worked on by thousands of programmers around the world. The story of how Git came to exist is a particular kind of story, the kind that programmers like to tell because it confirms something they already believe about themselves. The story is about how when programmers need a tool, they will, given enough motivation, build the tool themselves rather than put up with the tools that are available. The motivation, in this case, was a crisis in 2005 that affected the Linux project's existing version control system. For several years, the Linux project had been using a commercial version control system called BitKeeper, which had been developed by a small company in California run by a man named Larry McVoy. BitKeeper was, by most accounts, a very good piece of software. It had been licensed to the Linux project for free, on the condition that the Linux developers not try to reverse engineer the software or build a competing system based on what they learned about it. The arrangement had worked for several years. Then, in early 2005, an Australian programmer named Andrew Tridgell, who was famous in the open-source community for various clever pieces of work, decided that he wanted to build a free version of something like BitKeeper for use by other open-source projects that could not get the same free license that Linux had. To understand how BitKeeper worked, Tridgell did some careful probing of the BitKeeper servers, observing what kinds of data they returned in response to various requests. He was, by his own account, not reverse engineering the BitKeeper code itself. He was just looking at the publicly visible behavior of the system. But Larry McVoy, when he heard about Tridgell's work, decided that Tridgell was violating the terms of the free license. McVoy revoked the free license. The Linux project, with about a month's notice, was going to lose the version control system it had been using for the past several years. Linus Torvalds, by his later account, was furious about the situation. He thought Tridgell had behaved badly. He also thought McVoy had behaved badly. He did not, however, have time to argue about it. The Linux project needed a working version control system, and it needed one quickly. None of the available alternatives, in Torvalds' view, were good enough. The existing free version control systems were too slow, or too limited, or too poorly designed to handle the scale of the Linux project. They might have been adequate for smaller projects. They were not adequate for what Torvalds needed. So, in early April of 2005, Torvalds sat down at his kitchen table and started writing a new version control system from scratch. The principles he had in mind were specific. The new system had to be fast. It had to handle very large projects without slowing down. It had to be distributed, meaning that every programmer working on the project would have a complete copy of the project's history on their own machine, rather than relying on a central server. It had to support the kind of complex collaboration patterns that the Linux project required, where thousands of programmers were submitting changes that had to be reviewed and integrated by a smaller group of maintainers. The work took about 10 days. Torvalds, who was famously productive when motivated, wrote the core of the new system in about a week of intense work, and had a usable version running by April 7. He named the system Git. The name, in British English slang, means an unpleasant or contemptible person. Torvalds, by his own jokes, named his programs after himself. The first one had been Linux. The second one was Git. Git, in its initial form, was crude. It had a programming-style interface that was not designed for beginners. Many of its commands had cryptic names. Many of its error messages were obscure. Programmers who tried to learn it in those early days often spent days or weeks just figuring out how to do basic things. But Git was very fast. It was very flexible. It handled the demands of the Linux project. Within a few weeks, the Linux developers were using Git. The crisis with BitKeeper had been resolved. What happened over the following years was that Git, despite its rough edges, started to spread beyond the Linux project. Other open-source projects adopted it. Programmers at companies started using it for their own work. The features that had been built for the specific demands of the Linux kernel, like its speed and its support for complex collaboration patterns, turned out to be useful for many other kinds of projects too. By the early 2010s, Git had become the dominant version control system in the world. Part of Git's success had to do with a website called GitHub, which was founded in 2008 by a group of young programmers in San Francisco. GitHub was a website that hosted Git repositories. Programmers could put their code on GitHub, where it would be backed up and made available to anyone they wanted to share it with. They could also use GitHub to manage their projects by writing descriptions of what their code did, tracking bugs that needed fixing, and discussing changes with other programmers. GitHub turned out to be enormously useful. It became, over the following years, a kind of social network for programmers. Programmers used GitHub to find each other, to find code other people had written, to collaborate on projects with strangers, and to demonstrate their skills to potential employers. By the late 2010s, having a GitHub account with a substantial history of contributions was almost a requirement for getting a programming job at most companies. GitHub was bought by Microsoft in 2018 for $7.5 billion. As of these recordings, it hosts something like 400 million different projects in every programming language by something like 100 million different programmers. Git itself, the underlying tool, is still maintained by a small community of developers. Torvalds himself stopped working on it actively after a few months, handing it off to a Japanese programmer named Junio Hamano, who has been the main maintainer ever since. The tool has evolved gradually over the years, with new features added and rough edges smoothed off, but the basic design that Torvalds sketched in his kitchen in April of 2005 has remained intact. The thing the programmer types into their terminal to record a change in their code, the structure of how the changes are stored, the way the history is laid out, all of these are still substantially the same as they were in the first version. What version control gives a programmer beyond the practical benefits is something more like a psychological tool. It gives the programmer permission to try things. If you know that you can always go back to the previous version, you become more willing to make experimental changes. If you know that the history is recorded, you can examine your own thinking from a week ago and notice what you were trying to do. If you know that other people's changes can be merged with yours, you can collaborate without losing your own work. The whole activity of programming in the years since Git became universal has been quietly shaped by the existence of this small tool. The shape is not always visible, but it is there, in the willingness of programmers to try things, in the ease with which teams collaborate, in the way history accumulates instead of getting lost. It is worth spending a moment on what Git actually does, day to day for a working programmer, because the operations are simple, but the effect is large. The basic unit of Git is something called a commit. A commit is a snapshot of the entire project at a particular moment, along with a small message that the programmer writes to describe what changed. When the programmer makes a change to the code and decides to save the change, they create a commit. The commit captures the state of every file in the project at that moment, along with the message. The previous commit is still there, and the one before that, and the one before that, all the way back to the first commit the programmer ever made on the project. The history of a project in Git is a long chain of these commits. The programmer can at any point look at any old commit and see exactly what the project looked like at that moment. They can compare any two commits and see exactly what changed between them. They can, if they want, undo a recent commit and return to the state of the project before that change was made. The history is, in a real sense, time travel for the code. The programmer can move backward and forward through their own work. When multiple programmers are working on the same project, Git allows them to work in parallel by using something called branches. A branch is, conceptually, a separate line of development that diverges from the main line at some point in the past. Each programmer can work on their own branch, making commits to it, without affecting the main line of development or the other programmer's branches. When a programmer's branch is ready, the changes from it can be merged back into the main line, combining them with whatever other changes have been made in the meantime. The whole arrangement allows large teams to coordinate complex work without constantly stepping on each other's toes. One chapter to go, and a small closing. And then, quiet. The end of the story is in sight, though there's no need to rush toward it. If you've slept through whole sections already, that's exactly the right outcome. If you're still listening, that's also fine. The last chapter is the gentlest one. From here, the story winds down on its own. The voice will hand you off into whatever the rest of the night is going to be. Chapter 10. What it actually feels like. We have, by now, walked through most of the major pieces of what programming actually is. The programs, the functions, the control flow, the objects, the bugs, the libraries, the version control. Each of these is something that working programmers think about every day. Each of them was contributed, somewhere along the way, by one or more of the people we have talked about tonight. Together, they make up the activity that millions of people now do for a living, and that has produced the software you use every day without thinking about how it was made. To put a final shape on the picture, it helps to walk through what programming actually feels like. From the inside, when a programmer sits down to do it. Let us say that a programmer has decided to write a small program. The program does not have to be anything important. It could be a small program that keeps a list of books the programmer has read, or that calculates how much money the programmer has spent on coffee this month, or that converts temperatures from Fahrenheit to Celsius. Something small and personal. The kind of thing a person might write on a quiet weekend evening, more for the pleasure of writing it than for any practical need. The first thing that happens is that the programmer thinks about what they want the program to do. The thinking happens, often away from the computer, while walking, or showering, or staring at a wall. The programmer is, in this phase, trying to figure out exactly what the program should accept as input, what it should produce as output, and roughly how it should get from one to the other. The thinking can take minutes, or hours, or sometimes longer. The clearer the thinking, the easier the next phase will be. Most experienced programmers will tell you that this initial thinking is the part of programming that matters most, even though it does not involve any actual code. The programmer then sits down at their computer and opens an editor, a kind of text writing program designed for writing code rather than for writing prose. Modern editors have many features that help with programming. They color the different parts of the code so it is easier to read. They suggest possible completions as the programmer types. They flag obvious mistakes. The programmer chooses an editor based on personal preference, and the arguments about which editor is best are some of the longest-running and most pointless arguments in the programming culture. With the editor open, the programmer starts to write code. The first lines, often, are not the actual logic of the program. They are setup code, telling the programming language which libraries to import, which files to read, where to send the output. The setup code is boring but necessary. Most experienced programmers write it from memory or copy it from a similar previous project. After the setup, the programmer writes the actual logic. They write it in pieces. They write one small piece, then run it to see if it works. They write the next piece, then run that. The logic emerges gradually in the editor, growing line by line. The programmer is not, in general, writing the program from start to finish in order. They are jumping around, adding a function here, modifying a function there, going back to fix something they wrote 10 minutes ago. The activity, from the outside, would look almost random. From the inside, it has a shape, but the shape is the shape of the problem, not the shape of the code. After some amount of time, minutes, hours, or sometimes days, the programmer has something that they think might be working. They run the whole thing. It crashes. Or it produces the wrong output. Or it runs forever without ending. Some kind of problem appears. The programmer then begins to debug. They look at the error message, if there is one, and try to figure out what it means. They add code that prints out information about what the program is doing, so they can see where things go wrong. They reread the code carefully, looking for the mistake. They form a hypothesis about what is wrong, change the code to fix it, and run the program again. Sometimes the hypothesis is correct and the program now works. Sometimes the hypothesis is wrong and the same problem appears, or a new problem appears, or the original problem now manifests in a different way. The debugging continues. Each round of debugging in a well-going session is shorter than the one before it. The programmer learns with each round a little more about how their program actually behaves as opposed to how they had imagined it would behave. The gap between their imagination and reality gets smaller round by round. Eventually, the program does what they wanted it to do. This is the rhythm of programming. Write a little, run it, see what's wrong. Think about it. Change something, try again. The rhythm can be enormously satisfying. The puzzle of figuring out why the program is not working and then finding the change that makes it work has a particular pleasure to it that programmers, when they describe their work to non-programmers, often have trouble explaining. The pleasure is somewhere between the pleasure of solving a crossword and the pleasure of finishing a difficult novel. It is private. It is hard to share. It is one of the reasons many programmers find their work, despite the frustrations of it, deeply absorbing. After the program works, the programmer often spends some time cleaning it up. They rename variables to make the names clearer. They split long functions into smaller ones. They delete commented out code that they no longer need. They add comments that explain what the tricky parts do. They check the code into version control, so that the history of how the program came into being is preserved, and so they can go back to this version if they break it later. They might share the code with someone else, or post it on GitHub, or just save it on their computer for their own future use. Then they often, at some later moment, come back to the program. Perhaps a week later, perhaps a month, perhaps a year. They open it up again. They have forgotten by now much of what they were thinking when they wrote it. They reread it, slowly, trying to remember. The good code is the code that is still readable a year later, when the author has forgotten the original context. The bad code is the code that, a year later, the author cannot understand. Most programmers, when they look back at their own old code, have a particular feeling, a mix of pride at having built something, embarrassment at the specific choices they now find awkward, and gratitude for the parts they had the good sense to write clearly. That is, more or less, what programming feels like, from the inside, on a quiet evening working on a small program. The activity is part craft, part puzzle, part conversation with one's own past and future self. It is solitary, but, as we saw in earlier chapters, it is also profoundly collaborative. The libraries the programmer is using were written by other people. The version control system was written by someone else. The editor was written by someone else. The operating system was written by someone else. The programmer is, in some real sense, the last small contribution to a long line of work by other people, all of which is being combined in this moment to produce a small new thing that did not exist before. Closing. If you have stayed with this story from the beginning, and if you haven't, that's exactly as it was meant to be, you may have noticed something about programming that becomes clearer once you have walked through it. Programming, at its center, is the activity of writing down, with great precision, exactly what you want a machine to do. The precision is the hard part. The activity is mostly about that precision, about translating something you understand vaguely in your head into something the machine can follow without any ambiguity at all. The machine, unlike a person, will do exactly what you tell it. If what you told it isn't quite what you meant, the machine will do what you told it anyway, and the result will be wrong. And you will have to figure out where your instructions diverged from your intentions. Much of programming is the slow work of closing that gap. Every person in tonight's story was, in some way, working on this same problem. Each of them was figuring out a slightly different piece of it. Some were figuring out how to write the instructions down precisely enough for a machine to follow them. Some were figuring out how to make the language closer to how humans naturally think. Some were figuring out how to organize the activity so that many programmers could work together without stepping on each other's work. Some were figuring out how to make programs handle situations the programmer hadn't anticipated. Each of them contributed one piece, over the years, and the pieces, taken together, are what programming has become. What's quietly striking about the whole arc is how much of it was the work of people who, in their own time, had no idea what they were laying the foundation for. Ada Lovelace did not know she was writing the first program. The 6 women of ENIAC did not know they were inventing the profession of programming. John Backus did not know that Fortran would still be running, in some form, decades after his death. Margaret Hamilton did not know that the discipline she was creating, of writing software that handled situations its designers hadn't anticipated, would one day be the standard practice of an enormous industry. Each of them was working on a particular problem in front of them. The fact that the problems they were solving turned out, in retrospect, to be foundational was something only the later generations would be able to see. What you have, when a modern programmer sits down to work, is a vast and intricate stack of tools and ideas that other people have built over the past 180 years. The activity is, on one level, very simple. The programmer types into an editor. The text gets translated by a compiler or an interpreter into instructions the machine can run. The machine runs them. Something happens. On another level, the activity is impossibly elaborate. Every piece of the stack, the editor, the compiler, the language, the libraries, the operating system, the version control, the machine itself, was built by people, over decades, each of whom was solving some specific problem they had in front of them. The work of programming, when it is going well, feels like a small private conversation between a person and a very precise listener. The person says something. The listener does exactly what they were told. The person notices that what the listener did was not quite what was meant, and says something a little different. The listener does that. The person refines, the listener responds, and gradually, over many iterations, the person and the listener arrive at something the person actually wanted in the first place. The whole activity is, in some sense, the activity of being very careful about what you say. When it is going badly, programming has a particular kind of frustration that is unlike most other activities. The frustration comes from the gap between what you think the program will do and what it actually does. You read the code. You trace through it in your head. You see, you think exactly what should happen. You run the code. Something different happens. You look at it again. You still see what should happen. You run it again. The same wrong thing happens. The gap between your understanding and the reality is, in that moment, both invisible and large. The work of programming is, in some real sense, the work of slowly closing such gaps over and over for years at a time, until the day when, with luck and patience, the gaps get smaller and your understanding starts to match what the machine actually does. You don't need to remember any of this. You don't need to want to be a programmer. Most people don't, and that is fine. The work is not for everyone. It requires a particular kind of patience with one's own mistakes, a particular kind of tolerance for tedious detail, a particular kind of stubbornness when things are going wrong. The people who choose it, on the whole, tend to choose it because they enjoy it, in some private way more than they enjoy most other things. The activity has a way of selecting for a certain temperament. What might be worth carrying away, if you carry anything at all, is only this. The next time you use a piece of software, anywhere, on any device, you will know in some small way what is happening underneath. You will know that someone, somewhere, sat at an editor and wrote the code. You will know that they used libraries other people wrote. You will know that they organized their code into functions, and that those functions called each other, and that the whole thing was kept in version control. You will know that when something went wrong, they spent some hours staring at the screen, slowly closing the gap between what they wanted and what the program was doing. You will know that they are not magicians. They are people, doing a particular kind of careful work, with tools that other people built, on top of layers of decisions made by people who are mostly dead now. You will know, in other words, that programming is just an activity that people do. It is unusual in some ways. It involves a kind of precision that most other activities don't require. But it is not, when you look at it carefully, a mystery. It is one of the things human beings have figured out how to do over the last 180 years, and the things we have figured out, taken together, have built the small machines that surround us now. The next time you see a programmer at work, if you happen to, you will know, in some real sense, what is going on inside the room they are in. The screen will be full of text. The text will be a mix of words from English and symbols from mathematics, arranged in a particular shape on the screen. The programmer will be staring at it, occasionally typing, occasionally pausing. They will be, somewhere in their head, thinking through one of the activities we walk through tonight, imagining how a piece of code should behave, tracing through what it actually does, searching for the gap between the two, closing it one small change at a time. The room you are in is quiet. The lights, if you left them on, can stay on or turn off. The blanket, if you pulled it up, is still where you left it. The device you are listening through, whatever it is running a program right now, written by some programmer who you will never meet, made of functions and objects and libraries and decisions that go all the way back to the work of a young countess in London who, in 1843, wrote down the first algorithm intended for a machine that did not yet exist. The whole thing is still going. It will be going in the morning. Nothing in the rest of the world is asking anything of you right now. Sleep well.